As the use of mathematics became more complex, there was a need to express repeated multiplication in a more efficient manner. The trend in European mathematics during the 16th century was to make the expression of mathematical thought more concise. A notation was needed to allow an operation such as 5 times 5 times 5 times 5 to be written more efficiently. More importantly, with the development of algebra, a need existed to be able to write the product of an unknown quantity multiplied by itself. An early attempt at a new notation was accomplished by Raphael Bombelli in 1552. His method involved writing the coefficient of the variable and writing an arc above that number. In the arc would be written the power of the unknown. Using Bombelli's method, 3 times the square of an unknown quantity, 3x squared in our current notation, would be shown with 2 in an arc written above a 3. Today we would write 5x to the 4th, while Bombelli would write a 4 in an arc above a 5. A modification to Bombelli's notation was made in 1619 by Jobst Burgi. He replaced the arc, the number in the arc, with a lowercase Roman numeral. For example, the 3x to the second would be written by Burgi as a 3 with II, the Roman numeral 2, the lowercase Roman numeral 2 above it. And the 5x to the 4th would be written as a 5 with the IV, the Roman numeral 4, above it. The 17th century brought exponential notation to where it is today. In 1637, there's that year again, René Descartes, there's that guy again, wrote 3x squared as 3xx and 5x to the 4th as 5xxxx. In 1676, Isaac Newton modified Descartes' notation so that the power was written in the form that is still being used today. The only exception that was for some reason Newton desired xx instead of x squared. Eventually, the x squared was used as it is today. So basically, for over 300 years, we've used the same notation. Obviously, it works. Today, exponential notation appears to be very logical. And it took 100 years to develop that notation because things moved a lot more slowly, obviously, in the 16th and 17th centuries. We need to look at the patterns, we're back to patterns again, in powers of the various numbers. Okay, the two most important numbers in our number system are 0 and 1. Yet they provide a very boring pattern when you look at the powers of 0 and 1. If you listed all the powers of 0, you would have a sequence of zeros, because 0 to the 1 is 0, 0 squared is 0, and so on and so forth. 0 to any power is 0. The same can be said for the powers of 1. 1 to any power is 1, so therefore the sequence will be 1, 1, 1, 1. But this does raise an important point, that if you have a number that ends in 1 and you raise it to a power, the answer will also end in 1. And of course, if you have a number that ends in 0 and you raise it to a power, that answer will have a 0 in the last place. Let's take a look at the powers of 5 and 6 because they share an interesting common pattern. The powers of 5, and we've listed the first 6 powers of 5 and 6, you can see in the powers of 5 that they all end in 5. And starting with the second power, they all have a 2 in the tens place. And starting with the third power, the digit in the hundreds place alternates between 1 and 6. So it's pretty simple to probably figure out what the next power of 5 would be. If you have powers of 6, as we have here, showing the first 6, you'll notice that they all end in 6. And starting with the second power of 6, which is 36, there is a pattern in the tens place. We have 3, 1, 9, 7, 5, and this continues. 3, 1, 9, 7, 5, forever and ever. Patterns intrigue me. Patterns intrigue most mathematicians, and it's interesting to see that this pattern exists when we look at powers of 6, and of course the powers of 5 have a similar pattern. Also, it means if you have a number that ends in 5 and you raise it to any power, the answer will end in 5. If you have a number that ends in 6 and you raise it to a power, the answer will end in 6. Powers of 2 compared to powers of 8 show an interesting pattern, as do powers of 3 when compared to powers of 7. Notice, if you look at the ones place, you simply find that the powers of 2 end in 2, 4, 8, 6, 2, 4, 8, 6, and so on and so forth. All even endings, obviously, powers of 2 must be even numbers, but notice there's one even ending that's missing, 0. There is no 0 in an ending because a number that ends in 0 must also be divisible by 5, and no power of 2 can be divisible by 5. Notice the powers of 8. You look at the ones place, you have 8, 4, 2, 6, 8, 4, 2, 6. The exact same pattern as powers of 2, but backwards. Interesting. Powers of 3 and 7 have a similar pattern. 3, 9, 7, 1, 3, 9, 7, 1 for the ones place in powers of 3. Notice there's no 5. It's the only odd digit not present. And in powers of 7, the ones place is 7, 9, 3, 1, 7, 9, 3, 1. The same pattern, but reversed as the powers of 3. You also may notice that 2 and 8 are equidistant from 5, as are 3 and 7. The powers of 4 and the powers of 9 aren't very interesting because they really are a subset of powers of 3 and powers of 2. Okay, basically what you have in the powers of 4 are every other power of 2. 4, 6, 4, 6 are the endings. And in powers of 9, you have every other power of 3. The endings are 9, 1, 9, 1. The rules for operating, that is adding, subtracting, multiplying, dividing, numbers with powers, are similar to the rules we've used before, but they don't appear to be that way, and sometimes to many people they appear to be quite illogical. Addition and subtraction, we're not going to really get involved with. All you need to do there know is that you can only add and subtract numbers that have the same place value, the place value being a power and a base that are the same. We're going to look at multiplication and division. And these actually, when you look at them carefully, are quite logical. And then we'll use those results to come up with more abstract operating rules for other situations with powers of numbers, that is, numbers in exponential form. 3 to the second times 3 to the fifth means 3 times 3 times 3 times 3 times 3 times 3 times 3. Now that is 7 threes multiplied, which is 3 to the seventh. So 3 to the second times 3 to the fifth is 3 to the seventh. The rule is if the numbers have the same base, in this case 3, add the powers when you multiply. Not because it's an arbitrary rule that came down from the mountain, but the power tells us how many 3s we have. We add those powers up, and that gives us the total number of 3s that are being multiplied. By the way, you'll notice that if one of those 3s had been a 2, and we had 2 to the second times 3 to the fifth, we couldn't do that because we'd have 2 times 2 times 5 3s, and that wouldn't help. So the base must be the same, and we add the powers to multiply. Looking at a division problem, 4 to the sixth divided by 4 to the second. We have 4 times 4 times 4 times 4 times 4 times 4 divided by 4 times 4. We can cancel out 2 of those 4s, and we're left with 4 4s multiplied, which is 4 to the fourth. Obviously, the rule is if you're dividing two numbers with the same base, keep the base and subtract the powers. Not arbitrary, but based on what we see. Now let's take a look at some rules that aren't quite so obvious until you consider that they're based on the two rules that are obvious. Let's take a look at 10 to the second raised to the third power. Again, what does that mean? That means 10 to the second times 10 to the second times 10 to the second, which is a rule that says keep the base and add. 2 plus 2 plus 2 is 6. But wouldn't it be much easier than adding 2 plus 2 plus 2 to simply say this is 3 times 2, which is 6. When raising a base to a power, keep the base and multiply the powers. Remember the word power and the word exponent are the same. I just choose to use the word power since it's easier to say. The next few rules are even more abstract, but are based on the rules we've developed so far. The first we'll consider is, what does the zero power mean? It's logical to assume the zero power is nothing. That is, any number to the zero power is nothing. Since 2 to the first is 2, 2 to the 0 will be no 2's, which is 0. Wrong. Let's take a look at multiplication and division situations that will show us what the zero power means. We have 8 to the second times 8 to the 0. The rule for multiplication says keep the base and add the exponents. So, what do? 2 plus 0 is 2. We get 8 to the second power. Wait a second. We've multiplied 8 to the second and received an answer of 8 to the second. The only number in our number system that does that is 1. So 8 to the 0 must be 1. The division problem, 9 to the 7th divided by 9 to the 7th. Using the rule we said was quite logical, 9 to the 7 minus 7 is 9 to the 0. But dividing a number by itself can only be 1, and therefore 9 to the 0 must be 1. So therefore, any number to the 0 power other than 0 is 1. It may not make any sense, but it certainly works using the rules we've previously developed. How about negative powers? Well, let's multiply 6 to the second times 6 to the negative second, even if we don't know what that negative power means. Our answer, based on keeping the base and adding the powers, is 6 to the 0. We know that 6 to the 0 is 1. What do we call a number which, when we multiply it by a second number, we get 1? That number is called the reciprocal. So it's obvious that 6 to the negative second must be the reciprocal of 6 to the second. If we use the rule of division and we take 11 to the third divided by 11 to the fifth, we get 11 to the negative second. That is, 3 minus 5 is negative 2. But certainly dividing 11 times 11 times 11 over 11 times 11 times 11 times 11 times 11 would give us 1 over 11 to the second, the reciprocal of 11 to the second. Now, how about fractional powers? Well, let's use multiplication to see what a fractional power means. 11 to the 1/2 multiplied by 11 to the 1/2 must give us 11 to the first power, because 1/2 plus 1/2 is 1, and 11 to the first power is 11. So 11 to the 1/2 power is that number which, when multiplied by itself, gives us 11. Obviously, 11 to the 1/2 must be the square root of 11, and therefore the 1/2 power represents the square root. In fact, generally, a fractional power, x to the a over b, means the b root of x to the a. That is, the numerator of the fractional power is a power, the denominator is a root, no matter what the base is. Now, there are many applications using exponential notation. Exponential growth and decay is very common, and scientific notation is utilized to write numbers of great magnitude as well as exceptionally small numbers. We'll look at these applications right now. One common example of exponential growth is compound interest. You know, if you leave money in an investment for a long period of time, your money keeps growing at an ever-increasing exponential rate. Let's take a look at $1,000 invested at 8% annual interest, compounded quarterly, which means every 3 months, every quarter, you receive 1/4 of the 8% interest on the money in the account. And this keeps going on every 3 months as long as the money is in the account. What does that mean? At the end of the first interest period, you will have the original money, $1,000, plus 0.02, that is 2% of that $1,000, which is $20. The new balance will be 1.02 times $1,000, which is $1,020. The 1 in 1.02 means that's your original amount, and the 0.02, of course, is the interest you received on that amount. After 6 months, that is at the end of 2 quarters, the balance will be 1.02 times 1.02 times $1,000. This will be $1,040.40. Notice the interest received in the second quarter, $20.40, was more the interest received in the first quarter, $20. After 1 year, the balance will be 1.02 times 1.02 times 1.02 times 1.02 times $1,000. That is more easily written as 1.02 to the fourth times $1,000. It is convenient to write this in exponential form. Well, we may be concerned with a general rule, and that is, what about at the end of t quarters? T being a certain number, it's a variable. We can have it any number we like. Well, the way we would write that, obviously, is 1.02 raised to the t power, where t would be the number of quarters, times $1,000. Using this exponential notation, it is easy to compute the value of the investment at any period of time. After 10 years, which will be 40 quarters, the balance will be $2,200.04. After 20 years, that'd be 80 quarters, the balance will be $4,875.44. Leaving that $1,000 in that account for 40 years, which would be 160 quarters, you would have $23,769.91. Exponential growth, the compound rate of interest. Exponential growth and decay are easily modeled with an exponential function. The standard form is y equals ab to the x. X is your exponent, b is your base, and a is your coefficient. In this case, the lead coefficient, because it's the only coefficient. By the way, a is also the y-intercept, because when x is 0, b to the 0 we know is 1, and when x is 0, y equals a. Notice that if b is greater than 1, b minus 1 is the growth rate. So if b was 1.08, that would give us a growth rate of 8%. If b was 1.2, that would give us a growth rate of 20%. If b is less than 1, then b minus 1 is the negative number, and that would be the decay rate. What happens if b is 1? Well, if b is 1, you simply get a times 1 to the x, and we know that 1 to any power is 1, so we have a horizontal line, no growth. So you might say that 1 minus 1 is 0, and therefore b minus 1 tells us there is no growth. A good example of exponential growth is the expansion of federal expenditures on Social Security, Medicare, and Medicaid. The exponent for a reasonable model is about 1.14, meaning about a 14% increase, if you consider the years 1960 through 1980. Let's take a look at the data on the TI-83 to show us how we would recognize this is exponential. Here are the data on the social insurance expenditures of the federal government, 1960 through 1980, every 5 years. It is obvious by looking at the 5 points that the growth rate is increasing. That is, if you drew a line segment from the first point to the second point, and from the second point to the third point, etc., the slope of those line segments would be increasing. The growth rate is increasing in terms of the points, and therefore we have an exponential. As the increase continues to increase at an increasing rate, we have an exponential function. And therefore we could easily find an exponential equation that would model the behavior of the federal expenditures on social insurance. Some people would use that exponential model, the 14% growth rate per year, and extend it out and say by the year 2050 perhaps, we will need quadrillions of dollars to support that expense for 1 year. There's a problem there, problem alluded to earlier. We cannot extrapolate that far out. These are data from 1960 to 1980, useful to predict 1990, even possibly 2000. The fact is that things can happen, hopefully they will happen, to allow the growth in federal expenditures for Medicare, Medicaid, and Social Security to become an exponential growth, but at a lesser rate. But that remains for the politicians. A use of the exponential function in terms of decay, a good example of that is the half-life. A radioactive substance loses 1/2 the mass of its radioactive material every period of time equal to its half-life. The radioactive material becomes non-radioactive. This is, for example, how we know how to age something using carbon-14 dating. We know the half-life of carbon-14 as it changes from carbon-14 to a non-radioactive form of carbon, and a different isotope, as the physicists would say. The exponential model is y equals a times 1/2 to the x. A would be the beginning amount you had at time 0, and x would be based on the half-life, the number of half-lives, and therefore when you traveled through time 2 half-lives, you would have 1/4. 1/2 to the second power, you would have 1/4 of the radioactive material that you had when you started. So this is one common example of the use of exponential decay. Scientific notation takes advantage of the fact that our place value system is based on powers of 10. For example, the number 824,000, which is a fairly large number, can be written simply in scientific notation as 8.24 times 10 to the 5th. Scientific notation requires a number in decimal form between 1 and 10, multiplied by a whole number, an integer, I should say, integer power of 10. That power could be a positive integer, as it is here, or a negative integer, but it must be an integer. So we have 8.24 times 10 to the 5th. You'll notice that 8 is in the 100,000s place, 824,000, and 10 to the 5th is 100,000. For writing very small numbers, such as 0.00032, we also use scientific notation. Again, 3.2 times 10 to the negative 4th is a number, 3.2, between 1 and 10, multiplied by an integral power of 10. Now, notice that the 3 in our original number, in decimal form, is in the 10,000th place. And of course, 10 to the negative 4 is 1/10,000th. We can also use the scientific notation to multiply and divide, because remember, all scientific notation numbers have powers of 10. So let's take the two numbers we just had, 824,000, and multiply that by 0.00032. First, we write it in scientific notation form. 8.24 times 10 to the 5th times 3.2 times 10 to the negative 4th. Multiplying 8.24 times 3.2, we actually get 26.368. And multiplying 10 to the 5th times 10 to the negative 4th, keeping the base and adding the powers, we get 10 to the 1. But remember, in scientific notation, we want to write that number between 1 and 10, so we change the notation to be 2.6368 times 10 to the 2nd. That means the 2 must be in the hundreds place, so our answer to multiplying this rather big number by this fairly small number is 263.68. So scientific notation is helpful in writing large and small numbers, and also in operating, multiplying and dividing these kind of numbers. And again, when you get into areas like astronomy or microbiology, having scientific notation is a very handy tool. And of course, without the use of exponents, we would not have scientific notation. Every time we create an arithmetic operation, we create its inverse. So when addition was created, so was subtraction. When multiplication was created, so was division. You cannot have division without multiplication, nor can you have subtraction without addition. When we created the powers of a certain number, we talked about, for example, if we have 4 squared is 16, we knew we had this square root. And as long as we were raising things to the second power, we created the square root. If we were raising numbers to the third power, the inverse operation was the cube root. Now we've kept the base the same and raised it to different powers. What is the inverse operation if you have a base that you keep constant and you raise it to different powers and obviously get different answers? This inverse operation is called the logarithm. And if, for example, you say that y equals the log base b of x, and the b is written as a subscript, that means that x is obtained by raising the base b to the y power. In fact, the logarithm is simply the power, the exponent you must raise the base b to, to get the number in question. So again, y equals the log base b of x says that if I raise b to the y power, x is the number I'm going to get. If 10 to the fifth equals 100,000, then the log base 10 of 100,000 is 5. They are equivalent expressions, just like saying 7 times 6 is 42, and 42 divided by 6 is 7. If 2 to the eighth is 256, then we could write the expression the log base 2 of 256 equals 8. They are equivalent expressions. Logarithms were developed during the 17th century by a gentleman whose name is or was John Napier. He did this in 1614. And for many high school and college algebra and pre-calculus students, John Napier's name ranks among some of the scariest names in history because logarithms, for some strange reason, really bother people. Those of us who were going to school when Eisenhower was president remember that we use logarithms to do all kinds of operations that we could never have done because there were no calculators around, or the calculators that were around were either very, very expensive and certainly couldn't be carried in your pocket, and they had to be plugged in. And those of us who went on, as I did, to engineering college learned to use slide rules, which were, of course, were strictly based on logarithms. So Napier developed the logarithms, and a few years later, in 1622, William Outred used logarithms to create the very first slide rule. And slide rules lasted until the creation of the handheld, inexpensive calculator, probably in the mid-1970s, and have since disappeared, and now they're antiques. I still have my old slide rules. I never use them because the answers you get are not quite as accurate as what you get on a nice handheld calculator. But this started in the 17th century. In 1624, Henry Briggs realized the importance of the base 10 and started using logarithms that were base 10. These are called common logarithms. And in fact, these are the kind of logarithms that were used by those of us who have a bit of gray on our hair and went to school back, like I said, when Eisenhower was president, or even earlier than that. More recently, in terms of the use of logarithms, quite frankly, we've learned to use the logarithms whose base is e, the natural logarithm, the ln on your calculator, because many, many real-world situations can be explained with an exponential function where the base is e. Again, recall that e was the number that was named by Euler quite a few years ago. Now, we've talked about exponentials and briefly about logarithms, which are related to exponentials, and we've looked at a few examples, but perhaps we need to emphasize the importance of exponential growth and decay. For example, in biology, especially when you're looking at things like bacterial growth, we're talking about exponential increase. That is, the increase is growing at an ever faster rate. Population growth. In many parts of the third world, population growth is exponential, and therefore population growth for the entire world is exponential. And the question is there a maximum population that this Earth can handle? And if it is, how soon will it happen? A population model based on the exponential will tell us that. Sales growth of a new product, especially if it's successful, will be exponential. People hear about a product, from their friends who have the product, go out and buy it, tell their friends, and pretty soon we have many, many people buying the product. For example, VCRs. When they became priced where most people could afford it, the growth in the sales of VCRs was exponential, up to a point. The spread of disease, similarly, instead of telling your friends about a VCR, you sneeze at them and give them a disease. And that growth would be exponential in the beginning. Eventually, when everybody gets ill, there's no more chance for growth. And of course, fads. That's what a fad is. A fad is a rapid exponential growth of some habit or some clothing item or what it is. So exponentials are all around us. In the next lecture, lecture number 10, we'll begin to talk about calculus As this wraps up our discussion of algebra, calculus is next.